Hello AP Statistics students. Here is the video for the lesson we should have done on Tuesday. So to start from the beginning, hopefully you got a bit of an idea from the Khan Academy video what this is, but if you're still confused, I hope this clears it up. So the chi-squared distribution. We use the chi-squared for 3 different scenarios. The one we're going to look at right now is the goodness of fit. This one right here. That's what we're mostly going to focus on this video, but then there will be 2 others, homogeneity and a test for independence between variables. But we're going to focus on the goodness of fit one right now, and with this, we're going to actually calculate the chi-squared test statistic, and then also calculate the p-value. All right, so let's take a look at how this works. First, we now have 3 distributions. All right, we've got the normal distribution, of course. All right, looks like that. And for inference, we use the normal distribution. For our sampling distribution, when we do an inference of proportions, right? If we do a 1 prop z interval or test, we are using a normal distribution for the sampling distribution. If we are doing a t-distribution, well, that happens when we do an inference of means. So remember, the t-distribution is very similar to the normal distribution. All right, it's almost exactly the same if your degrees of freedom are high. All right, if you have a large sample size, a high degree of freedom, then it's basically normal. However, if you have a smaller degree of freedom, the tails get wider and the peak isn't quite as high. All right, this is exaggerated, but hopefully you get the idea there. And here, that's if you have a small sample size when your degrees of freedom are small. Those are the 2 we've used before. Oh, and that one was for an inference of means, right? Inference of means. Quantitative variables. All right, well, today, right now, what we were going to try to look at before is the chi-squared. So the chi-squared looks a little bit different. It also depends on your degrees of freedom. So here, this blue one here is if a degree of freedom of 1. That doesn't happen very often, though, right? Usually we have a slightly bigger sample. So take a look at what happens. So a 4 is this red one, and an 8 is this, bluish green one here, teal or something like that. It's not normal. It's not even symmetric. It's skewed to the right. But we use it in very much the same way that we use the others for inference. So a lot of this should look familiar. So the chi-squared test for goodness of fit. So here's a scenario where you would use this. Are your M&Ms actually correctly distributed by color? I know it keeps me up at night too, right? Man, got to make sure my M&Ms are distributed in the correct color and that they have peanuts inside, because don't give me any of that other crap that doesn't have any peanuts inside. That's terrible. Peanut M&Ms are the only way to go. So Mars Incorporated claims the following ratios are used when making M&M candies. All right, it's right here. These are the ratios they claim they use when making M&Ms. You, of course, doubt this. Always doubt. You take a random sample of 60 M&Ms to see if your results fit their model. Now, we know our results won't be exactly the same as their model. If it's truly a random sample, there's going to be sample variability. It won't be, quote unquote, perfect. All right? The chi-squared is going to give us an idea of how rare our sample would be if this is in fact true. Okay? Based off of sample variability alone. So we take our sample. Okay, over here is our observed sample. This is what we actually got. We got 3 reds, 7 yellow, 9 green, 9 orange, 20 blue, 12 brown. Now, using their ratios, however, how much would we have expected to get in a quote-unquote perfect bag of M&Ms? Well, 12.5% are red, okay? If 12.5% were red, and we took a sample of 60, well, what's 12.5% of 60? So our expected value would be 7.5. So we would expect in a sample of 60 to have 7.5 reds. Now, I know you can't have 0.5 of an M&M, right? But because this is theoretical for the expected, you are allowed to have decimals. All right, it's not a integer number. It doesn't have to be because this is theoretical. Now, your observed, these all definitely have to be integers because you counted M&Ms. You can't count half an M&M unless you're eating half an M&M, and that's just weird. All right. So the expected are allowed to be decimals. So that'd be the same for yellow, right? Because that one's also 0.125. So that's the same. So this will be 7.5. We expect 7.5 yellow, 7.5 green. Oh, but orange was different. 25%. Did you know they have different percentage? So 25% orange and 25% blue. I'm not making this up. I saw this. Yeah, more orange and more blue, apparently. So what is that? So it's 25% of our sample size, 60, because we took a sample of 60. Ideally, 25% of those should be orange, so 15. So that's both for blue and orange, right? 15 and 15. And then brown is also 12.5%, so that one will also be 7.5. Now, as you can see, it's not perfect, right? We didn't exactly get this. All right, we got 3 reds when we expected to have 7.5. So now the question is, well, is this discrepancy just sample variability? Yeah, all right, just sample variability. It's a random sample, so we expect it to be off a little bit. Or are these numbers so far off that we doubt what the company told us? All right, hopefully you see the makings of a hypothesis test here, where this is our null hypothesis, and our alternative is that the null isn't true. Now, I'm not going to do all that right now. We're not going to do the whole state, plan, do, conclude, conditions, and null and alternative hypothesis. Not going to focus on that right now, but that is where we're going. Right now, we're just going to focus on calculating the chi-squared test statistic so that later we can use it. All right, so we're just going to do the calculation part right now. So this is the sample we got, and this is the ideal expected value. So how weird is our sample? Well, to figure that out, this is the formula we use. Okay? The chi-squared test statistic, the number that tells us how weird, how unlikely almost is our sample, here's how you calculate it. You take the observed value, all right, that's from your sample, and you subtract the expected value. All right, how far off was it? But sometimes your observed is the bigger number, sometimes your expected value is the bigger number, and that means that result would be positive and negative sometime. Well, when we combine all of this, right here, when we combine it all, we don't want those to cancel out. We want the negatives and the positives to sort of both influence how weird our sample is, and that's why we square it. It gets rid of the negatives, much like a standard deviation does as well, right? And then, so that big numbers don't unduly sway things just because they are big numbers, We divide by the expected value as well. We do that for every single piece of data, every single category, and then we add them all up. And that is our chi-squared number. So let's do this here together. Yes, eventually our calculator will do this for us, but I think it is good for us to do the calculation by hand at least a couple times. So, 7.5s and 15s. That was 7.5, 7.5, 7.5, 15, 15, and 7.5, right? All right, so let's do this. So our chi-squared, so it's like an x, but a little bit curly. That is the Greek letter chi. And it's squared because this is all coming from squared numbers. So the chi-squared test statistic. So for our first piece of data, the red ones, well, it's 3 minus 7.5 squared divided by 7.5 plus, now our next one, now the yellow, 7 minus 7.5 squared divided by 7.5. Now the green, 9 minus 7.5 squared divided by 7.5 plus orange. Ooh, orange is a little bit different, right? So that one will be 9 minus 15 this time squared divided by 15. That one had a different expected value, right? I'm just going to continue underneath here. So 20 minus 15 squared divided by 15 plus, that was blue, now brown. So 12 minus 7.5 squared divided by 15. No, 7.5. What am I doing? So that will give us our chi-squared test statistic. Okay, so I'm going to type all this into the calculator. I'm going to pause my video. You can pause the video and type all that in. I don't know if you need to actually watch me do that. So I'm going to trust that you type that in yourself. All right, I did it. So I typed that whole thing into the calculator right here, and I got 9.8. All right, bring that up again real quick. I got a test statistic of 9.8. So my chi-squared is equal to 9.8. Bull, what the heck does that mean? Yeah, we don't know what that means yet. It does seem like a very arbitrary number at first because we don't know a whole lot about the chi-square distribution yet. And if you can never spot check this just by looking at a chi-square and you're like, oh, that's big, that's small, that doesn't really matter too much. Because the calculator will always sort of do it for you on our next step. Okay? And so you never really have to interpret this number with your own intuition. The calculator will do it for you on the next step, which is calculating a p-value from that chi-squared. A p-value from the chi-squared. So what happens is there's a chi-squared distribution for this, and it is somewhat, well, quite a bit skewed to the right. And so this chi-squared distribution is based off of how many degrees of freedom our scenario has, okay? And the degrees of freedom, shocker, is n minus 1. But this time, n is not the sample size. N is the number of categories. All right, N is the number of categories. So in this case, we have 1, 2, 3, 4, 5, 6 categories in all, 6 colors. So our degrees of freedom will be 6 minus 1. So our degrees of freedom is 5. And that is all we need to define what type of chi-squared model we have. As you saw up here in this picture, every chi-squared for degrees of freedom is slightly different. Okay, and so when if you ever want to try to spot check this 9.8 as a chi-squared, well, that rarity depends on the degrees of freedom, and it's just makes it a little more complicated to spot check in your mind whether 9.8 is a big number or a small number for you. But the one way you can sort of spot check it in your head is, all right, I don't like I'm going to make it more skewed, okay? That's a little better. All right, the peak of a chi-squared is always degrees of freedom minus 2. So the peak for this chi-squared distribution that has a degrees of freedom of 5 will be at 3. Which then it's like, all right, well, if the peak is at 3, 9.8 is going to be pretty far over here, isn't it? So my boundary of 9.8 is going to be pretty far over here. So what are the chances of getting something that big? Oh, that should be a little familiar. What are the chances of getting a number, a chi-squared 9.8 or bigger? Is that area right there. And while you have never done this before, you should know exactly what's coming next. We need to do a chi-squared CDF. A chi-squared CDF. And yes, your calculator has that. Second distribution, not the PDF, the CDF. There it is, the chi-squared CDF. It's got that little X looking thing, a squiggly X. The calculator does as best it can with the few pixels it has. That is the chi-squared CDF. All right, you've got the lower, upper degrees of freedom. So our lower is 9.8. Our upper, well, it goes to infinity, so a really big number. And our degrees of freedom, 5. And we get 0.08%. Well, 0.08 or 8%. So our p-value is 0.08. Let's take a look at that on the Casio real quick. The Casio is quite a bit nicer in some ways because it draws it for you, which is kind of cool. So we go stats, distribution, chi CDF. I want to change list to variable. The Casio apparently can do this straight from the list if you just type the numbers in, which is kind of nice. But we're going to go variable because we have the chi-squared already. So the lower was 9.8. The upper is a really big number. Oops. The degrees of freedom were 5. And now if I scroll down, it will draw it for me. And as you can see, that's a pretty, my drawing's not that great, but it's still the same drawing, right? And we get the same p-value though, 0.08. So again, that is the probability of getting a sample like ours okay? Now when I say a sample like ours, that the statistical translation is a chi-squared that is greater than or equal to 9.8. All right, that's how weird our sample is. All right, how far off the null or the expected value is our sample of a chi-squared of 9.8. The probability of getting a sample like ours, assuming the expected values are true or are legitimate, are true slash legit, all right, aka the null hypothesis is true, but we'll get to that when we actually start doing the full problem. But so there's by sample variability alone, there would be an 8% chance of getting a sample that's this far off. Okay? As far off as ours. So if we take all the differences, square them, divide by the expected, that's accumulating how far off our sample is from the expected value. And there's an 8% chance that we could get a chi-squared of 9.8 or greater simply based off of random variability, sample variability, random chance, however you want to say that. And yes, eventually, we are going to take that p-value and compare it to an alpha, right? Now, we didn't set all that up right now, but we'll compare it to an alpha and then either reject or fail to reject the null hypothesis based off of that. But hopefully that kind of gets you an idea of what the chi-squared is. All right, here's the equation one more time. Here's how we wrote that whole thing out. That's what I want you to be able to do and understand right now because, to be honest, the calculator is going to start doing a lot of it for us. Okay? I hope that clears up what you watched in the Khan Academy today. If not, make sure to ask me some questions.